Okay, now let's start today's class. And so, so now we are in the chapter 4 of processor. So in this chapter, actually we will go into the world of computer hardware. So actually in chapter 2, we learned about the RISC-V assembly instruction, and also we also learned about the machine code translated from the RISC-V instructions, right? So it's still software. So I think you may be it's tricky to understand some assembly instructions, because we are familiar with the high-level languages such as Python or C, but the assembly instructions are kind of low-level instructions, low-level programming language. So it's also language, right? For the machine languages, right? So it's a low-level language, so it may be tricky to understand this low-level language because we are not familiar with this low-level language. Okay, but you need to understand the high-level language codes are translated the instructions. So actually, these instructions. It's an assembly instruction first, and then its assembly instructions are also encoded. So encoded is the machine code, and then actually the hardware can only understand the machine code. Okay, so that's why we learned about some low-level language not to understand the computer system, overall computer system. Okay, so now in chapter 4, we will learn about the hardware architecture finally. So as you can see in this slide, so this is this slide shows the several layers of computer systems. Actually, I showed this figure in the first class of this course, right? Do you remember? So in chapter 2, we learned about the instruction set architecture. So actually ISA, it's called ISA. So ISA is around here, okay? So traditionally when we mention computer architecture, then it means the instruction set architecture. Actually, it's a very old religion, right? So, and then now, so we will focus on the hardware architecture. And then this hardware architecture is called microarchitecture. Okay? It's a microarchitecture. So we will focus on the microarchitecture of a computer system. So the layer, so actually the level is also goes down, goes lower. Okay, it's a lower than the instruction, assembly instructions or machine instructions. So it may be more difficult because, as I mentioned, we are not familiar with this low-level world. Okay, so we are not familiar with the hardware world, but in order to understand the entire aspect, actually, we need to focus on the performance of computer systems because you are learning about the computer engineering and computer science, right? So we need to focus on the performance and then efficiency and then some other facts when we study about this area, this research area. So we need to understand some microarchitecture layer of the computer system. It's a hardware architecture of a processor. Okay. So let's review what we learned in this course. So in chapter 1, we learned about the performance of computer systems, right? So what is the equation? The execution time is instruction count multiplied by CPI multiplied by PC is clock period, right? And then instruction count instruction count is influenced by our software code, right? And algorithm and compiler. Also, the ISA, the instruction set architecture also influences the number of instructions, number of compiled instructions. So, in order to increase the performance, so we need to reduce the instruction count, right? But we also need to learn about the other aspects regarding the performance of a computer system. So what are they? CPI and PC, clock period. So these factors are determined by hardware. Okay? So CPI can be also changed by software, but it is actually it is because instructions exhibit some different CPI values. Okay? But the CPI of an instruction is majorly determined by hardware. So in order to increase the performance, so we need to reduce the CPI, also we need to reduce the clock period. So that's why we need to learn about the hardware architecture and hardware aspect of the computer system. So in chapter 4, we will focus on the hardware. Okay, so in chapter 4, firstly, we will learn about the simplified version of the RISC-V processor. It's a simplified, okay, for this course. And then firstly, we will learn about the single cycle. Okay. In chapter 2, we learned that the high-level codes are translated into instructions, right? RISC-V instructions. And then we just focus on the number of instructions for considering the performance of the code. So that means we assume that every instruction consumes the constant time. Okay, so it means that every instruction takes one clock. So firstly, we will learn about the dispersion. So which means that every instruction takes one clock period. It's called a single cycle processor. Single cycle processor. And then we will learn about the more realistic process architecture. It is called a pipelined processor. So it is because so if we just implement this simple single cycle processor, we cannot reduce the clock period. Also, so actually clock period is also very critical for the performance of a computer system. So with the pipeline architecture, then we can reduce the clock period of the processor. Okay. So that's why we will learn about the pipeline architecture in this course. So actually, as I mentioned in the first class of this course, pipelining is a very important concept. And so you need to understand about the pipeline architecture. So it is because it's the core knowledge you need to get from this course, right? Very important, pipeline architecture. Okay, so in chapter 4, that's what we assume that our RISC-V processor just provide the several instructions. I mean, part of RISC-V integer instruction. Okay, so it is because so we need to simplify the architecture of the processor. So that's why we assume that our processor just supports only the part of RISC-V instructions. But as you can see, these instructions include every category of instruction, right? Memory instructions, our processor will support the load word and store word, and then for the arithmetic or logical instruction, our processor will support the add, sub, and or, and then control instruction, branch instructions. Okay, so I assume that the processor will support BQ, branch if equal. Okay. Okay, so this is the what we learned in chapter 2. So this is the concept of a processor. So let's review this concept of the processor. So this is a processor. So instruction is given. So we learned about the instruction in chapter 2, right? So you need to remember, right? So instructions are given. So this is instruction, and instruction is given to a processor. So that means that an instruction becomes an input data. So it's an input. Then what are outputs of this system? The outputs are, output is change of state. Change of state. Then I mentioned that if the instructions are executed, then what are changed? Register files or main memory. So PC is also included. So because the branch instruction also modify PC register, the program counter. Right? So the data in register files and main memory are changed by instruction. So this is a result of instruction in a processor. Okay, so this is the somewhat simplified version. Actually, this is related to the software engineer, or software developer. So in chapter 4, we will focus on the inside of a processor, right? So we will learn how these data are changing by executed instructions. Okay, then so we will learn how. So this is the result. So in chapter 2, we learned about the result of instruction, and then in chapter 4, we will learn how these results are generated by a processor. Okay. Okay. Then let's see what are required for executing instruction. Okay. So let's see some example. So add x1, x2, x3. So these are source registers, RS1 and RS2, and then this is a destination register, and then this is instruction. This is an instruction. So let's see how this instruction is executed. So which processing? So let's see what are required. So firstly, in order to execute a certain instruction, then we need to identify program counter of a target instruction. Right. So in chapter 2, so program counter is the address of this instruction, because so we can find instructions in memory, right? And then also we learned that if we just see the dump, it's the assembled code, you can find some PC part, right? So every instruction is mapped to the program counter value. So which means that if we just set the current program count, so if we just set the program count for a certain instruction, so let us assume that this PC is the 0x100. So if we just set the PC of this instruction. So that we just set PC as the 0x100. Then processor automatically, right? Automatically read this instruction from memory, okay? Using this PC. So PC is an address for an instruction, okay? So this instruction is read. So it is called the instruction fetch. So firstly, an instruction needs to be read from the memory. And then for this process, we need to set the PC value. Okay, and then this process is called instruction fetch. Then, if this instruction is fetched from the memory, this is the binary data, right? So this is machine code. So this should be machine code like 0001111 Okay. Actually, this machine code is given to a processor. So what is required? So once this data is read from the memory, then we need to figure out which instruction is encoded. So firstly, the processor needs to decode. Okay. So I mentioned that the encoding is the assembly instruction is translated into machine code. This is called encoding. And then decoding means that the processor figure out which instruction is in this machine code, and then what are the destination registers, or what are the source registers. So this process is called decoding. Okay. So instruction is read. Instruction is given to a processor, but this instruction is binary data. So this binary data needs to be decoded. Okay. Decoding is also required. So I'm explaining what are required for executing instruction. So then if we see this instruction, so if the instruction is decoded, then a processor can figure out, oh, this instruction is add instruction. And then, oh, this is the R type instruction, right? So if we just see the copy code, then we can just figure out the type of instruction. And, oh, this is the add, and then RD is the X1, RS1 is the X2, and then RS2 is the X3. So this is the register number. Okay. Then what are required? What is required? So operation of this add instruction is X1 equal X2 plus X3, right? So for this operation, a processor needs to read data from register file, right? Because in order to execute the add operation, we need to get the data operands from the register file, right? So which means actually the registers are very small memory inside our process, right? So which means that the data are stored in registers. So in order to perform this operation, then the data needs to be read from the registers, okay, using the register number. Okay, so register reading is also required. Register read, register here. Then what is required? So data is ready. So required data are ready for execution. And the next step is execution, right? Because the data is ready, the data is read from the registers, and then data is ready, then we can execute addition. Okay. So in chapter 3, we learned about the basic arithmetic hardware, right? So adder, subtractor, or multiplier, divider, right? So using this hardware, so we can perform arithmetic operations. Right? So this is the add operation. So using adder, we can perform x2 plus x3. Then result is generated. Right? So this is called execution. And then actually the process unit for execution is called on ALU, the arithmetic logic unit. Okay. So the result is generated. And what are required? What is required for the next step? So the result needs to be stored in the X1 because this add instruction just changes the target register, destination register X1. So the result is generated by ALU, the execution unit for hardware. Then this result needs to be stored in the register. Okay. So this is these are the required steps for executing instruction. So I just explained about the add instruction, but if this instruction is the memory instructions such as load word or store word, then the load word, if the load word is executed, then the data is to be read from the memory. And then if the store instruction is executed, then the data is stored into the memory. So actually the memory needs to be accessed. So memory access is also required. So why? So why did I explain about this? Because this is some steps, the required steps for executing instructions. So actually in chapter 2, we just learned the result of instructions only, but in chapter 4, so we will learn how the instructions are executed. So I just explained what are required. So what is the required steps for executing instruction? So these steps are required. Okay? So it means, so this is the hardware, right? It's not software. So the hardware needs to perform these steps. Okay? So which means we need to understand how hardware performs these required steps for executing instructions in chapter 4, right? So that's why I just explained what are required steps for executing instructions. Okay. Okay, so then we will learn about the hardware architecture and hardware design of processor. So before going into the process architecture or micro architecture design, we will just review the logic design conventions. So the first, the processor is also a big kind of this system. Okay, so then we need to understand about some logic design concept or some digital design concepts for understanding some design process for computer processors. Okay, so it is just a review of the digital design course, digital logic design course. Okay, so logic design basic. So digital system just handles the binary data, but this binary data is represented using the voltage level of the electric circuits, right? So binary digital system just handles the binary data, and which means that each bit has only two cases, 0 and 1, right? 0 and 1. But we can represent 0 using the low voltage or ground. Okay, it's a ground. And then we can represent the 1 using the high voltage level, which VDD. Okay. So you can, so what is VDD? So if you just actually, so recently, so you just use a smartphone or some tablets. So actually, it's not easy to look inside of the look at the inside of the, some computer system. But if, actually, maybe 20 years ago, we frequently assemble the computer system. We purchased some components like the CPU, RAM, and other disk drives and board. Yeah, we can just assemble the computer system using these components. So when the CPU is assembled, then we need to set down the supply voltage. So this supply voltage is kind of 1.0 volt. So this voltage is actually VDD. Okay, it's the supply voltage. And then ground is the 0 volt. Okay. So using the voltage level, we can represent the binary data for 0 and 1. Then also digital circuit means that digital circuit just process is binary data 0 and 1. Okay, and then it can also generate some result. Also, these are also binary data. So what is the digital system? Digital system is that it receives the digital data, so 0 and 1, and then also it generates the digital data result, okay, 0 and 1. So this is our digital system. And then when we build a digital system, then we can classify the electric circuits into the combinational element and sequential element. Okay, so if you took the digital logic design, you need to understand about the combinational element and sequential element. So what is a combinational logic or combinational element? So combinational logic is that, so input is given, so input is also a digital input. Okay? Then output is generated. Output is only generated by input signals. Okay? So this is the definition of combinational logic. Output is just a function of input. Okay, but we can get this output at some delay delta t. Okay, so this is the circuit. So this is, and the circuit works in a real world, right? So it means we can observe delay. Okay, if we live in the real world, and we can observe the time, right? So it's also same for the hardware. Hardware works in the real world. So which means that, so this is the combinational logic, but the combinational logic is the this is the definition of the combinational logic. So output is determined by only input signal, but at some time. So output is generated after some time by input data. This is a combinational logic. Okay. Then what is the sequential logic? What is the sequential element? The sequential logic, actually the output of the sequential logic is determined by input and stored information. Okay? Stored information. Okay? So this is the sequential logic, and then combination logic. Output is just a function of input. But for the sequential logic, the output is determined by input and previous states. States means the stored information. So this is the definition of sequential element. So actually, by combining sequential logic and combinational logic, then we can build a digital system, right? A digital circuit. Okay, let's see the examples of combinational elements. So these are the examples of combinational elements: AND gate, adder, multiplexer, and arithmetic logic unit. So this is ALU. Okay. So what is the AND gate? So this is some equation, the logic equation. So y equal a, logical and b. So this is the symbol. Okay. So y is the some logical and so this logic, this combinational logic just performs the logical and operation for each bit, bit a and bit b. Then it generates the output y. So adder is an adder. So it performs the addition. And then what is the multiplexer? Based on the selection signal, then y, the output y can be connected to the one of inputs. Okay, so in this case, so if S is 0, then y is connected to the I0, right? Then if S is 1, then y is connected to the I1. This is the definition of multiplexer. Then ALU just performs the function using two input data. Okay, so actually, in chapter 4, we will use the actually these elements. So, I posted the third level assignment of Blackboard, right? The Blackboard. So actually, you need to design a simple combinational logic. Actually, it's a very simple logic gate using system value. So system value is hardware description language. Okay, it's called HDL, hardware description language. Okay, so it is used for designing a digital system because it's hardware description. Okay, so actually for upcoming several design apps, so you will be requested to design a simple RISC-V processor using system variable. Okay, so in this slide, so I just show the example of system value module or system value code. Okay, so this is the example of AND gate. Okay, so this is the AND gate. Okay, so if you see that this AND gate, the AND gate has two inputs A and B and one output. So inputs and outputs are also called ports. Okay. So this is the interface of this module. So it receives input signal from input port, and then it generates output signal using output ports. So in the system Verilog module, this is the module name, and then ports are just declared like this, and then as you can see, A and B are input ports, and Y is on output port. So this is the one bit signal. So the width is not represented. Then we can easily implement the AND gate using Y equal A and B. So this is the bitwise AND operator of the system Verilog. Okay, then that's it. So this is the AND gate. And then adder. So in this example, so this is the adder. So as you can see, adder has also two input ports and then one output port, right? But as you can see, the this input signal A has 8 bits. Okay, because in order to represent the very large number, then we need to use multiple bits, right? So actually, this module represented there are two input ports, but the width of a single input port is 8 bit. So bit number 7 down to bit number 0. And then output, the width of the output port is also 8 bit, right? Then what is the grid? What is the statement? A equal A plus B. Because this is adder, right? Okay, so multiplexer. So if you see the multiplexer has two inputs, three inputs, including this selection signal, and then one output. So I0, I1, S. So you can implement the multiplexer like this. So here, so I0, I1, and S is just the selection signal. Then the output. Also, in this example, the input port is the multi-bit port. Okay. So, what is the statement? So, Y equal output equal if S is same to the 1, 1, and Y is connected to the I1, otherwise connected to the I0. So this using this statement, we can implement multiplexing using system Verilog. Okay, those are the examples of combinational logic. Then let's see the example of sequential logic. So in this example, I just introduced the E flip-flop. So it's because actually when you mention the sequential logic, actually we frequently use D flip-flops. Okay. Then what is the D flip-flop? So this is the symbol of D flip-flop. So if you see that this symbol, then D flip-flop has two input ports and one output port. So you can find the clock is here, and then D means the data input, and then Q is the data output. Okay, so this is the clock signal. Then what is a clock signal? Actually, we learned about a clock signal in chapter 1, right? So clock is the rectangular waveform, right? And then this rectangular waveform is repeated. So 1 is here, 0 is here, 1 is here, 0 is here, and repeated with the same period. This is the TT. This is a clock signal. So, D flip-flop receive is clock signal. Okay? Then what is the behavior of this flip-flop? So this is waveform just shows the behavior of the flip-flop. So behavior is actually at this so this is called a rising edge of clock. So it means that the clock signal is just changed from 0 to 1. So that's why this is called a rising edge of a clock signal. So in the D flip-flop, at the rising edge of the clock signal, it samples the value of D. So at this point, it samples, okay? And this signal is reflected to the Q, okay? But after some delay, because this is also a circuit, okay? But we can say that in the D flip-flop, the input D is sampled at the rising edge of the clock, and then this sampled value is reflected to output Q. So this is the behavior of D flip-flop. So as you can see, the value D is changed here, but output is not changing. It is because this value is sampled at the rising edge of the clock. So at this point, this changed value is sampled here, and then this value is just reflected to the Q. So this is the behavior of D flip-flop. And then actually in the design, these D flip-flops are frequently used. Actually, in the pipeline architecture, we use the D flip-flops. Okay. Also, we can use some enabled D flip-flop. So which means that this sampling is enabled only when the enabled signal becomes 1. Okay. So this is the enabled D flip-flop. Okay. So in this example, so D flip-flop samples the value of D, but it is enabled. So it's a right signal. So Q is updated by D. But how about this point? Even though at the rising edge of the clock, the enabled signal is 0, so which means that the sampling is not enabled. So output is the same. Output is 90. Okay, so this is the enabled D flip-flop. So this D flip-flop is the sequential logic, right? So what is the output? The output of this D flip-flop is Q, and we can observe that Q is just determined by past data. Okay, so at this point, the Q maintains some data. Okay, Q stores the data. So that's why this flip-flop is the sequential process. Okay, so let's see the mechanism of clock. The clock methodology. So I mentioned that in order to build a logic, what is the circuit, then we combine both combinational logic and sequential logic. And then actually we use flip-flops and combinational logic. So it is because we build a digital circuit or digital system like this. So what can you observe? So we can observe, so in this model, so in this model, we can find combinational logic here, right? And then it is called a state element 1, but actually this is the D flip-flop. Also, it's a state element 2, also this is actually D flip-flop. So it looks like this. It's a clock signal. So this is the clock signal. It's actually the same clock. Then this is E, and then this is Q, this is D, and this is Q. And then between these two D flip-flop, we can find the combinational logic. So we can build on this system like this. Right. So then let's see the behavior of this model. Okay. So we can find that the input of this combinational logic is the output of D flip-flop, right? And then I mentioned that this output is updated at the rising edge of the clock. Okay? Rising edge of the clock. Then, what can you observe? So this is the rising edge of the clock, right? So at this point, Q is updated. The Q is updated. So Q1, Q2, Q3. There can be multiple Qs or multiple data. So actually, for the input of this combination logic, the input of this combinational logic is determined right after this clock edge, the rising edge of the clock. So do you understand? So actually, the combination logic can have multiple inputs, right? But in this model, these input ports, the input signals of combinational logic is the output of D flip-flop. So which means that at the rising edge of the clock, so this rising edge of the clock, the output Q of this D flip-flop is just determined just at the rising edge of the clock. Just right after the rising edge of clock. Okay. So it is stabilized at the same time. Okay, you understand? So this is called synchronization. It's similar to the synchronization, the same kind of thing. It's called the synchronization. So which means that all input values for this combinational logic are stabilized just right after the rising edge of the clock, right? Then we can observe the output of combinational logic is connected to the input of this D flip-flop, right? So, and then I also mentioned that combinational logic has delay at the T. So which means that the output of this combinational logic is stabilized after delta T, and then which means that the result is generated by this input, but it's synchronized input. So after delta T, then this output is also sampled by another D flip-flop. Okay, so this signal is also synchronized by this clock edge, the clock signal. So when we build this the system, all signals, most signals are synchronized by clock signals. So we synchronize the all input signals for this input of combinational logic. And then if the output is generated, and this output is also sampled, also synchronized by clock edge. So we just build the system like this. Why? Because we want to make a system stable. Okay, we need to control the system. And so which means that all signals need to be synchronized and then it's processed, and then also the output is synchronized and processed again and again. It's very similar to the conveyor belt of a factory, right? So all jobs are synchronized. Okay, so this is also this scheme is also applied to the pipeline. Okay, then how can we determine the clock period? So this is the system model. There is a delta T. So there is a deep flip-flop here, and then there is a deep flip-flop here, and then all signals are synchronized by this deep flip-flop. And then actually I mentioned that the combinational logic has delay delta T. And then I mentioned that after delta T, the output is stabilized. The output is generated. And then this output signal also needs to be sampled by rising edge of the clock. So actually, the clock period. So we need to set the clock period, right? When we build a digital system. But I mentioned that input is synchronized. The input will stabilize at this point, and then after some delta T, then output will be generated. This is the out. And then this out is also sampled by the next clock edge. So the TC clock period is to be larger than delta T. Right? It's obvious, right? Because I mentioned that after the output is generated by combinational logic, this output data needs to be sampled by this edge, the next edge of the next rising edge of the clock. It means that clock period needs to be larger than the delta T. So which means delay of combination logic determines the clock period. You understand? So it's also same for a computer processor. It's also same to the computer processor. It's because a computer processor also requires clock. Okay? And then which means that this clock period will be determined by this delta T, the delay of combination logic. And then also we learned that execution time is proportional to the TC clock period. So which means we need to reduce the TC to improve the performance of a computer system, right? How? Oh, we need to reduce delta T, the delay of combination of between deep flip-flops. Okay, that is some basic knowledge for understanding the performance of a processor, a computer hardware, right? You understand? Okay. So, which means that so we also need to use deep flip-flops for implementing RISC-V processors. Okay, RISC-V processors are also digital circuit. So which means that we can implement the RISC-V processor using system value. So this is the system value code that can implement in flip-flop. So as I mentioned, it has three ports, the clock input, and then D and Q. And then the clock is the 1-bit signal, and then as you can see, D and Q has the 8-bit width. Okay. So this is the behavior of deep flip-flop. So in order to implement a deep flip-flop, so we need to use the always underbar FF. So FF represents the flip-flop. Okay. So you need to use the always underbar FF state 1, and then it works. So it samples at the rising edge of clock. So it's also called the rising edge. It's a rising edge. So actually it is also called the positive edge. Okay. And then in the system value, we need to use the positive edge, the POS edge, for representing the rising edge of a clock. So at the positive edge of a clock, then it's a sample, and then output is updated by D, the input. Okay, so this is the behavior of D flip-flop. So if we just write a system value of state 1 like this, then we can deal D flip-flop. Okay, so this is this, and then this is called a D flip-flop with clock and reset signal. So what is reset? So reset means so we make the output 0. It's called reset. Okay. So reset signal, with the reset signal, the output is initialized as 0. Okay. So this is the example of the flip-flop with negative reset. So negative reset is that if reset is 0, then output becomes 0. Okay. Why? Because usually if we just set the control signal as 1, so it means that this control is named. But sometimes we need to the control signal is named. We need to make the control signal is named if the control signal value is 0. Okay. So that in this case, it is called the negative control signal. Okay. So in this example, this is the reset signal, but reset signal is enabled if this signal becomes 0. So that's why this signal is called the negative reset. So it means that if the signal value becomes 0, then the output is reset. So in order to implement the negative reset, then we need to add the neg edge of reset signal. And then if the reset signal is 0, then as you can see, output becomes 0. Okay, then otherwise, if it is not reset, then the output is updated by input signal also at the rising edge of the clock. Okay. And then this is the example of a flip-flop with names. Okay. So what is the added? This part is added. So if enable is 1, then output is updated by input signal. So actually this is the example code of latch, but we need to avoid latch because it is generate. Actually, a latch is the kind of bug in the design. So which means it means that we need to avoid generating latch. Okay, this is the example code. Okay, so this is some basic knowledge for basic knowledge for this design. Okay, so if you are not familiar with the design concept or a system value, then I recommend you review some my previous lectures. So actually, I also recorded detailed logic design lectures in the previous semester. So I will also provide some links for this previous detailed logic design lectures. Okay. Okay. Then how can we? So this is so until here, because this is some basic knowledge required for digital design, required for implementing digital design, and then using this knowledge, then we need to implement the RISC-V CPU or RISC-V processor. How? So actually, I explain how instructions are executed, right? And then I also explain which steps are required for executing instructions. So in order to implement the RISC-V processor, then we need to implement these required steps using hardware or using system value, right? So this slide shows the conceptual view of the RISC-V processor. So that actually the required steps are just represented using rectangular modules, okay, modules, and then we just connect the input and output ports of the modules, okay, and then so I briefly explain. So you can find the PC is here. Why? What is the purpose of this PC? So this is the program counter register. Okay, so PC. And then I mentioned that the firstly we need to set the PC value for the target instruction, right? So and then using this PC, then we need to access the memory to read the target instruction, right? So this is the PC, and then this is the output of the PC. Okay, the output of the PC is the PC value. As you can see, the PC is connected to the address port of the memory, and then this memory is called an instruction memory because it has instructions. Okay, and what can we get? If address is given to a memory, then we can get data, right? So for this, so what is the data of the instruction memory? It's instruction, right? So PC is given to an address port of the instruction memory, and then we can get instruction. Okay. So this is the instruction fetch step I explained, right? The PC is given, PC is set, and then PC is given to the instruction memory, then we can get instruction. Okay, this is the instruction fetch step, and then the instructions are decoded. This instruction needs to be decoded. Then I mentioned that using like the x1, x2, x3. So we need to read data from the register. So actually, I mentioned that the registers are also kind of small memory, the kind of memory. So this group of registers is called register files. Okay, so it's a group of registers. We can find the registers here. Okay, so register number is given. If the register numbers are given to the register file, then we can get operands. Okay, required data. RS1, RS2, right? Then, it's an execution, ALU. So RS1 data and RS2 data is given to ALU, then output is generated with the result. So for the add instruction, the result is stored in the register file. Okay, registers. So this result is given to the register file again. Okay, it's given to the register file. But for the load instruction or store instruction, then we need to access the memory. So actually, we can generate the address of load word or store word using ALU. Okay, I will explain later. Then this address, the calculated address is given to data memory. Okay, so for the load word instruction, if the address is given, then we can read the target data, right? Then the target data is also stored in the register file. Okay, so actually, so we just define or required hardware module, okay, like the instruction memory, registers, ALU, and data memory, okay. Then we just connect the input and output ports of these modules, right? And then, as I explained, these modules are required for the steps. The steps I explained, the steps for executing instructions. Then what is this? This is the adder, then this is for. So PC is also updated by PC plus 4. So which means it's the next instruction. Okay. Also, PC can be updated by branch BQ. So this updated part is also required. Okay. So this is the PC for the next instruction, and this is the PC by branch instruction. But so actually, this implementation is not possible, is it because? So actually, we need to build electric circuit, right? So the electric circuit, so think like some wire. So if wire is connected like this, then all parts of these wires have the same thing. Okay? What's the problem? Oh, in this part, then this value is B1 and this B2, and then B1 is actually different from the B2. The value of this wire is different from this wire. So actually, this is not possible. Okay? So in this part, actually the wire is connected like this, but it's not possible in the digital circuit. So actually, we need to use the multiplexer here. So actually, it is not here, but we need to use the multiplexer here. So which means that if there can be two inputs, and then we need to select the output from the two inputs or multiple inputs, then we need to use a multiplexer. Okay. So here and here and here. Okay. So actually, the wires cannot connect it directly in this case because the input values are different. Okay, so actually, and then in the next class we will learn how to build a data path. So these are called the data paths. And then before completing today's class, I will briefly explain about the third lab actually. So in the third lab, you need to use the EDA tool, the design tool called a validator. Okay, so which means that you need to install a validator on your WSL or Ubuntu. Okay, and I believe you already installed the Ubuntu in the first lab, right? So then you can easily install the validator here and just follow these steps for installing validator. Also, I provide this end module and then test bench file. Okay, so you can compile the this end game using, and then you can also run the simulation of the end game with the test bench. And just follow these steps, and then you can get the value from here. So you need to design the exclusive or adder and subtractor. But you can just modify this design, right? Then so you can just modify this test bench. And then if you feel difficult for doing this lab, then you can post questions on the blackboard, or so you can ask here. Okay, I will stop here. Any questions? Thank you for your attention. See you in the next time.